Hello everyone, my name is Pambo. Today I'm very happy to present our work at ICACT 2026. The title of our paper is FRAB-MAC, a reliable adaptive broadcast MAC protocol for mobile UACNs. This work was jointly conducted by Guo Zhichuan and Liu Yating, and all of us are from Institute of Acoustics, Chinese Academy of Science. I will introduce our work from 5 aspects, and they are background and contributions, mathematical models, detailed design of FRAB-MAC, simulations and results, and conclusion. The last part is the reference. First, I will start with the background and our main contributions. In recent years, rapid advances in UV technology have greatly expanded their application in ocean exploration, environmental monitoring, and resource inception. To improve data collection efficiency and expand exploration range, multiple AUVs often cooperate as a formation, making reliable and timely information exchange essential. This places strict requirements on the underlying underwater acoustic communication networks among all network layers. The MAC protocol plays a critical role in determining how node access the limited acoustic channel and directly affect network performance. Existing underwater MAC protocols can be broadly classified into contention-based and contention-free protocols. However, contention-based protocols suffer from high collision probability and low channel utilization, while FDMA and CDMA are limited by bandwidth constraints, the near-far problem, and high complexity. As a result, TDMA is widely adopted in underwater acoustic networks due to its simplicity and inherent collision avoidance characteristics. However, TDMA still suffer from the silent node problem caused by unsuccessful reception of control packets. The workflow of central TDMA MAC protocols consists of several steps. First, control node determines the transmission order and the slot length for each node. Second, control node broadcasted this scheduling result, called the transmission sequence. Third, normal node then transmits its data accordingly, with the status information embedded in the data packets. If the control packet is lost, normal node cannot obtain their slot assignment and therefore remain silent to avoid additional collisions. This is known as the silent node problem. To address this issue, AB-MAC proposed a chain-based recovery strategy. Each node embedded the time slot information of its successor in the transmission sequence into its data packet. In this way, even if the control packet is lost, subsequent nodes can still recover their time slot assignment, which significantly reduces the number of silent nodes. Based on the recovery strategy, we read the following questions. Can the control node generate a more reliable transmission sequence? In this work, we enable the control node to generate a more reliable transmission sequence. The main contributions of our work are as follows. We design a new objective function that integrates a scoring-based reliability factor in the evaluation of transmission sequence, guiding heuristic algorithm to drive reliable scheduling results that enhance the robustness of recovery strategy. FRAB-MAC introduced a FHO-based frame optimization algorithm that determines reliable transmission sequence and slot length, addressing the joint optimization problem of minimal frame length and network reliability. Simulation results demonstrate that FRAB-MAC significantly reduces the number of silent nodes and effectively improves network throughput. The second part introduced the mathematical model used in this paper. First, we described the transmission path loss model, where the absorption coefficient in dB per kilometer is calculated using the SWAP equation. Next, we introduced the packet transmission probability model. We first compute the signal-to-noise ratio in linear scale, and then drive the average bit error rate and the packet success rate. By calculating the packet success rate between every pair of nodes, we finally obtain the success probability matrix. The third part of the presentation introduced the detailed design of our protocol. The proposed FRAB-MAC protocol is designed for fully connected UV information networks with the objective of reducing certain nodes, avoiding impact collisions, and improve network throughput. The main workflow is illustrated as follows. After topology discovery, the control node obtains the distance matrix and the PSR matrix. Based on the information, it generates the transmission sequence using the phi Hog optimizer with a new objective function. The output of the FHO is the transmission sequence with the minimal objective value. The control node then broadcasts the scheduling result. Finally, the ordinary nodes transmit their data according to the assigned schedule. Before the initialization phase, nodes have no prior knowledge of the position of their other nodes. During initialization, all nodes broadcast their current position and future trajectory information in a random order using conventional centralized TDMA. To avoid packet calculations, each time slot is designed to be long enough to accommodate a standard data packet, as well as the maximum propagation delay. Based on the received information, the control node computes the pairwise distance between nodes and constructs the distance matrix. Using the PSR formula introduced earlier, the control node further estimates the pairwise packet success rate and drives the transmission success probability matrix. In a normal mobile AUV information network, regardless of the transmission sequence generated by the control node, each node can reliably obtain its assigned transmission order and slot length directly from the control node, and the internode recovery mechanism does not influence whether a node stays silent. However, when node 2 gradually drifts from the information to perform a specific task and moves further away from the control node, as shown in the right figure, the increased distance makes the link between node 2 and the control node unreliable. Since the relative position of node 1 and node 3 with respect to the control node remains unchanged, the reliability of any transmission sequence is primarily determined by whether node 2 can successfully receive the control information. The reliability factor is defined as a cumulative score of a transmission sequence computed based on the estimate PSR between adjacent nodes. If the PSR between current node and the S node, and the PSR between the S node and its immediate processor in the transmission sequence exceed their respective thresholds, the node is able to acquire or reconstruct its slot information from the control node or its predecessor, thereby avoiding silence. In this case, the score is incremented by 1. If both fell below their respective threshold, the node is very likely to lose control information and remain silent. Therefore, the gain is 0 and the score is unchanged. And the max attainable RS is n-1, because the control node must always occupy the first slot of each frame to broadcast the scheduling result. Here we list all possible transmission sequences. In the first case, node 2 occupied the second slot. Since there is no preceding node to recover the scheduling result, the reliability factor is 2. In the second case, node 2 transmits after node 1, but the link between node 1 and 2 is highly unreliable. The reliability factor remains 2. In the third case, node 2 transmits after node 3. The link between node 1 and 3 is reliable, so the reliability factor increased to 3. Sequence 4 and sequence 6 are examples of reliable transmission sequences. To optimize both the frame length and network reliability, we introduced a new objective function based on FRAB-MAC's minimal frame length function. Here, n-1 is the maximum reliability factor RS, and n-1 minus RS measures how unreliable a sequence is. The original objective function is a minimization problem, which minimizes the frame length. By minimizing n-1 minus RS, we effectively improve the reliability of the sequence while still maintaining as a minimization problem. The frame length is calculated using the same formula as in AP-MAC, following the collision-free condition proposed in the original work. The FHO-based optimization process for the transmission sequence includes several main steps. It starts with the initialization, generating a random permutation of n nodes. Then each candidate sequence is evaluated using our new objective function that considers both frame length and reliability. Then comes the grouping step, where several praise are assigned to each firehawk. After that, the position of the firehawk and praise are updated according to the FHO rules to generate a new population. The process of the evaluation and the position updating is repeated iteratively, with the global best solution update constantly. At the end, the final global best solution gave us the optimal transmission sequence. This part we introduce the simulation and the results. We evaluate the performance of the proposed FRAB-MAC, AB-MAC, and a conventional centralized TDMA, known as CTDMA protocols, with MATLAB in this part. The UV nodes are randomly deployed within a 3D underwater area of 4 by 4 by 4 cubic kilometers and maintain the initial random formulation while moving linearly at a speed of 5 knots. In addition to ambient noise, burst noise is also considered in the simulation to evaluate its impact on data packet transmission and reception. Burst noise is assumed to obey a presumed distribution with parameter lambda, which indicates the frequency of noise event. We assume that if burst noise occurs during the reception of a packet, the reception is considered unsuccessful. For fair comparison, both the genetic algorithm and the FHO are initialized with a population size of 100 and run for up to 100 generations. To ensure the robustness of the results, 40 independent trials were conducted for each network size and node density. 3 key metrics are considered in the simulation to compare the performance of different MAC protocols. The first metric is the average frame length, defined as the mean duration of a TDMA cycle. The second metric is the average throughput per node, defined as the ratio of total amount of data received by all nodes to the product of the simulation duration and the number of nodes. Third, the average number of silent nodes per frame, which reflect whether the optimized transmission sequence can reliably guarantee that every node has successfully received the broadcast control packet. From the left figure, it can be observed that for the same number of iterations, FHO coverage faster than the genetic algorithm while solving the frame optimization problem, as reflected by its constantly lower frame length. To provide a simple measure of computational complexity, we further compare the runtime of a single execution of each algorithm. FHO also requires less computation time than GA. The dashed line indicates the average runtime, which is 1.05 seconds for genetic algorithm and 0.87 seconds for FHO under our experimental setting. Therefore, the proposed FHO-based frame optimization algorithm outperformed the GA-based one in terms of both coverage speed and the computational efficiency. The result of the left figure indicates that FRAB-MAC achieved a shorter average frame length compared to AB-MAC, with an average reduction of 12.57%, as shown in the right figure. FRAB-MAC constantly achieved the highest throughput, followed by the AB-MAC, and CTDMA exhibits the lowest, regardless of whether the date rate is 1,700 bps or 3,070 bps. On average, FRAB-MAC improves throughput by 15.06% compared with AB-MAC. Although AB-MAC employs an improved genetic algorithm to drive the transmission sequence, its optimization capability declines as the network size and the number of nodes increase, making it difficult to obtain a near-optimal solution. In contrast, FRAB-MAC, guided by the FHO and the scoring-based reliability factor, exhibits a stronger global search capability under same iteration conditions, generating shorter and more reliable transmission sequences that lead to highest network throughput. It can be seen that by introducing a new objective function that jointly optimizes throughput and reliability, FRAB-MAC significantly enhanced the success rate of chain-based recovery mechanism, thereby reducing the number of silent nodes. Under lambda is 0.1. The average number of silent nodes per frame is 0.11, compared to 0.779 for AB-MAC and substantially lower than that of CTDMA. Even under higher burst noise level, FRAB-MAC constantly maintains fewer silent nodes. For instance, when lambda is 0.3 and 0.5, the average are 0.89 and 1.45 respectively, both markedly lower than AB-MAC's 1.6 and 2.14. Here are the main conclusions of our work. This paper proposed FRAB-MAC, a FHO-based reliable adaptive broadcast MAC protocol for underwater AUV formations. By redefining the FHO objective function, FRAB-MAC incorporates a scoring-based reliability factor to ensure that all nodes successfully receive the broadcast schedule from the control node, effectively overcoming the limitations of AB-MAC's control message recovery strategy. Simulation results demonstrate that FRAB-MAC outperforms AB-MAC and conventionally centralized TDMA by achieving stronger average frame lengths, reducing the number of silent nodes, and significantly improving the network throughput. Here's our reference list. This is part of the reference list, and this is the other part of the reference list. Thank you for all your attention.